The second type of bonding we're going to look at is covalent bonding. A covalent bond results when atoms share electrons in such a way that each atom has an octet of electrons in the outer orbital. Again, we're trying to satisfy that octet rule, and there's a couple ways to do it. We just saw how to do that with ionic bonding. With covalent bonding, rather than electrons being transferred, they're going to be shared. So after sharing electrons, each atom will have a completed outer orbital. For example, two hydrogen atoms can share their single electron. So if we're recalling back to electron orbitals, the first one holds up to 2 electrons. After that, for simplicity's sake, we're looking at how they can hold up to 8. So hydrogen, again, we were looking at one of the most simple atoms there with a single proton, single electron. So the hydrogen gas becomes a diatomic atom. That means di just meaning 2, diatomic 2 atoms. One hydrogen binds to another hydrogen atom, and we have this single covalent bond. So here we can see the representation of how those electrons are shared. You can draw it this way. Shorthand, the structural formula, it's showing you that covalent bond. You'll see a single line. So if you're kind of thinking that there's an electron on either side, representing 2 electrons there. The molecular formula is the shorthand that you'll see probably more often, but doesn't give you much information about the bond itself. So it relies on some of your other chemistry knowledge so that you know how those atoms are held together. So not only can you have a single covalent bond, you can also have a double covalent bond. You can even have a triple covalent bond, but we'll just look at single and double for now. So with oxygen, so having 2 electrons in the first orbital, so we're keeping in mind that they're sharing here. So 2 are coming from this atom, these 2 are coming from the other atom. So normally had 1, 2, 3, 4, 5, 6 in its outer orbital, right? So in order to satisfy so that they both have 8, they can share these 4 electrons. And this forms a double bond, which is shown by our 2 lines here. Even though these different ways to represent bonds are useful for us being able to comprehend how electrons are either shared or transferred, these structural formulas make it seem as if molecules are one-dimensional. Molecules, in actuality, have a 3-dimensional shape that determines their biological function to a large extent. Molecules with 2 atoms are going to be linear, so similar to how we just saw hydrogen gas or oxygen gas. Molecules such as methane with 5 atoms are going to have a tetrahedral shape. So methane is also a gas, and looking at how we have covalent bonds here in the sharing of electrons can be represented here in that structural line formula, or CH4. And so when we look at that, it looks like it's flat, but in actuality, it's more tetrahedral shape. And so you'll see the ball and stick model or space filling model to help us comprehend that. With covalent bonds, they can be nonpolar or polar. And so if the sharing of electrons between 2 atoms is fairly equal, you have a nonpolar covalent bond. If we're thinking of the term polar, and if you have like a polar political candidate or a polarizing issue, you're putting things either or, right? So with a polar bond, you have electrons that spend more time around one atom than another. So our good example of a polar covalent bond is with water, because we have an unequal sharing of electrons. Electronegativity is the attraction of an atom for electrons in a covalent bond. Some atoms are naturally more electronegative than others, and so electrons end up spending a greater amount of time around those atoms. I'll show you. So nonpolar covalent bonds, we've got a fairly equal sharing of electrons. It's not as though these electrons are going to spend more time around one hydrogen atom than another here. They're fairly equally shared. Similar to methane, it's mostly equal. as in the electrons spend about as much time around each atom. So hydrogen, oxygen, methane, all nonpolar covalent bonds. But with water, we have an unequal sharing of electrons. Oxygen is more electronegative than hydrogen, and so this results in electrons, which are negatively charged, spending more time around that oxygen atom than around the hydrogen atoms here. What we see is this partially negative oxygen and a partially positive hydrogen. This is what we mean by a polar covalent bond. What we can also see here with water, even though we write it H2O and might think of that as linear, water in actuality has this bent shape, and that, along with its polarity, is going to contribute to how it acts and a lot of the properties of water, which we'll get into later. If you think of these pairs of electrons kind of pushing hydrogen down to make that bent shape, that might be useful. Now that we've looked at how water is a polar covalent bond, we can talk about hydrogen bonding, because this attraction between water molecules is a really good example of hydrogen bonding. Polarity within a water molecule causes the hydrogen atoms in one molecule to be attracted to the oxygen atoms in the other water molecules. The attraction is between partially negative oxygen and partially positive hydrogen, and it's this attraction that results in a hydrogen bond. So hydrogen bonds are weak individually but strong collectively. If we're looking at this representation of water and we're remembering that it's polar and that this oxygen atom has a partially negative charge because electrons spend more time there, compared to the partially positive charge of hydrogen, this is your hydrogen bond that results. So again, that attraction between slightly negative, slightly positive. This hydrogen bonding is what causes surface tension in water, and it's also what holds things together in a DNA molecule. We'll look at that later as we go along.